This is Sally. She's an artist with a dream and a brush in hand. After years of selling her paintings at local markets, she finally took the leap and launched her very first online store, sallyshop.test. Every corner of the site is her own creation, from the homepage layout to the hand-picked fonts. It's a digital reflection of her art, built with care. To protect her customers and their login data, Sally added what she believed was a strong security feature, a CAPTCHA. Now, bots and hackers can't just brute force username or passwords, she thought. They'd need to be human to get past the CAPTCHA. But what Sally doesn't know is that even the strongest looking locks can be opened if they're built wrong. And this is where Kim comes in. He is an ethical hacker, a penetration tester hired to find security flaws before the real criminals do. Today, Kim will probe the login form on Sally Shop, and he's about to prove that this CAPTCHA is far from unbreakable. Let's dive in. But first, you might be wondering, what exactly is a CAPTCHA? CAPTCHA stands for Completely Automated Public Turing Test to tell computers and humans apart. In simple terms, it's a test that tries to block bots by asking something humans can solve easily, but machines can't. You've probably seen them everywhere. Things like, click all the pictures with traffic lights, type the wavy letters you see, or solve this simple math problem. The goal? Prevent automated abuse, like bots spamming forms, brute forcing login pages with tools like Hydra, or scraping data. In Sally's case, she added a CAPTCHA to her login form. That way, even if someone had a list of usernames and passwords, they'd need to solve a new CAPTCHA for every single login attempt. And that's supposed to stop automated brute force attempts entirely. But here's the twist. CAPTCHAs can be defeated. And Kim is about to prove exactly that. To launch this attack, Kim is going to use Python, the hacker's multi-tool. But first, he needs to make sure it's installed. So he opens a terminal and types Python double-version. And there it is. Python 3.13 is installed and ready to go. Next, Kim creates a clean workspace for this project. He makes a new folder called CAPTCHA, where he'll write all his code. Inside this folder, Kim creates a virtual environment to isolate his project dependencies. This keeps the environment clean and avoids conflicts with other Python projects. To do so, he types python-m venv, followed by the name he chooses for the environment, here CAPTCHA_nv. This command creates a folder named CAPTCHA_nv, containing a standalone copy of Python and tools just for this project. And voila, the environment is now created. Next, Kim needs to activate it. To do so, he runs source, the name of the environment, then bin activate. And just like that, his terminal is now working inside the virtual environment. Anything he installs will stay inside this little sandbox. For an easier and more interactive experience, Kim installs Jupyter Notebook, a tool that lets him write and run code in the browser, perfect for testing small scripts step by step. Jupyter Notebook is installed by running pip install notebook. As you can see, it installs a lot of packages. These are the components Jupyter Notebook needs to work properly. After a short moment, voila, it's installed and ready to use. But Kim prefers something a bit more modern, so he also installs JupyterLab. This is done by running pip install JupyterLab. And voila, the installation finishes much faster because most of the required components were already installed when he set up Jupyter Notebook. Think of JupyterLab as the upgraded version of Jupyter Notebook. It's like a lightweight integrated development environment in your browser. You can write Python code in notebooks or .py scripts, open terminals, file browsers, and even run Markdown, all inside a single elegant interface. With everything installed, Kim can launch either Jupyter Notebook or JupyterLab. But as mentioned, JupyterLab is the more modern option, so he launches JupyterLab. And there it is, his hacking cockpit. From here, he can write Python scripts to solve CAPTCHAs, inspect web requests, even run terminal commands, all without leaving the browser. Kim clicks on the notebook icon, and a fresh Jupyter Notebook opens inside JupyterLab. He right-clicks on the Notebook tab and renames it, let's say, as CAPTCHA. Now he's ready to start writing code. But first, he needs to make sure the notebook is using the right Python interpreter, specifically the one inside his virtual environment CAPTCHA_env. In Jupyter, this interpreter is called a kernel. You can always see which kernel is active by checking the top right corner of the notebook. Right now, it shows something like Python 3 IPy kernel. But what does that mean? A kernel is the actual Python process that runs your code. It's the engine behind the notebook, the part that executes cells and returns output. When you install Python with Jupyter, you get a default kernel, usually named Python 3 IPy kernel. If we click on this kernel, a window opens. In the selection dropdown, we notice that Kim's virtual environment, CAPTCHA_env, is missing. To make it appear as an option, Kim needs to register his virtual environment with Jupyter. To do so, he opens a terminal. Make sure his CAPTCHA environment is activated, and run python m ipy kernel, install username, followed by the name of the environment. Then display name to specify the name that will appear in Jupyter's kernel selection menu, here Python parentheses, CAPTCHA_env parentheses. As you can see, the installation is quick. Kim goes back to the notebook, clicks the kernel name in the top right corner again. And this time, there it is. Kim virtual environment is now listed. He selects it, and now his notebook is fully connected to the virtual environment he set up earlier, with all the tools he'll need to break the CAPTCHA. To crack this CAPTCHA system, Kim will rely on 4 main Python libraries. Each one plays a specific role in his attack, and together, they give Kim the power to automate what Sally thought only humans could do. The first library is requests. This library lets Kim's Python script act like a browser. It can load web pages, submit login forms, manage cookies, and more. Then PyTesseract, a Python wrapper for Tesseract, one of the most powerful open-source optical character recognition engines. This is what Kim uses to read the text from the CAPTCHA image. Just like your brain looks at an image and sees numbers, Tesseract can do the same, but in code. To work with images in Python, Kim uses Pillow. Finally, there's Bytes.io, a handy utility from Python's input-output module. Kim runs this first cell to check whether the libraries import properly. As you can see, there is an error, no module named PyTesseract. Python is telling Kim that it doesn't recognize the name PyTesseract. That's because even though he created a virtual environment, he hasn't actually installed the PyTesseract package inside it yet. To install PyTesseract, the command is simple: pip install PyTesseract. But what if you don't know the exact pip command? No problem, you can just Google pip followed by the name of the library. Then select the PyPI result. That's the Python package index. There, the correct command is shown right at the top. Kim can just copy that, then go back to the terminal and runs pip install PyTesseract. The installation is quick, and you might notice something interesting. Alongside PyTesseract, it also installs Pillow automatically. That's because PyTesseract depends on Pillow to handle images. In Python, packages can have dependencies, and when you install one, pip installs all the others it needs to work properly. Now that everything is installed, Kim goes back to his notebook and runs the first cell again. This time, no errors. Everything imports successfully. Kim's environment is now ready, and he's about to fetch and solve the Sally's CAPTCHAs. To do that, he defines the 3 key URLs his script will need. The first one is the base address of Sally's online store. It points to the home page. Every other page Kim needs to access, like the login page or the CAPTCHA, is built off of this base URL. The second one is the login page. This is where users submits their username, password, and CAPTCHA code. It's the endpoint responsible for verifying credentials and deciding whether to let someone in or not. If Kim goes to the Sally login page, he can see the URL he needs, sallyshop.test/login. That's exactly the one he uses in his code. And finally, there's the CAPTCHA image URL. Now you might be wondering, wait, is it normal for a CAPTCHA to be a URL? The answer is yes, absolutely. In fact, that's how most CAPTCHA systems work behind the scenes. The login page usually contains an image tag like this. That tag points to a server endpoint, a special URL that generates the CAPTCHA image on the fly. Every time the browser, or in Kim's case, his Python script, visits that URL, the server returns a new image with a randomly generated code embedded inside. This approach keeps the login page clean and dynamic. The CAPTCHA image is loaded separately and is often tied to a session, cached for a limited time, and invalidated after one use. So yes, it's not just common, it's best practice to serve CAPTCHAs as dedicated image URLs. And that's exactly what Sally's site is doing. It generates a new image from the CAPTCHA endpoint every time someone visits the login page and serves it to the user. The last part of this cell just prints each URL so Kim can make sure everything is set correctly. As you can see, the URLs for the home page, login page, and CAPTCHA are now correctly defined. Now, Kim is ready to interact with the site, but like a real browser, he needs to maintain a consistent user session across multiple requests. To do this, he can simply use the requests module imported earlier. This module has a powerful feature called session that does exactly that. This single line of code is more powerful than it looks. By calling request.session, Kim creates a persistent session object. It acts like a browser, keeping track of cookies, headers, authentication state, and most importantly, the server-issued user session ID. Why is this critical for CAPTCHA attacks? Well, without a session, every request Kim sends would look like it's coming from a brand new user. For example, when Kim sends a GET request to the login page, the server might assign him session ID 227 and generates a CAPTCHA image tied to that session. If Kim then submits a POST request with a username, password, and the solved CAPTCHA, and does not use a persistent session, the server sees it as a completely new session. A new session is created, maybe session ID 228, and the CAPTCHA value stored in session 227 is no longer valid. That would break everything. Because the CAPTCHA image Kim downloaded was tied to session 227, but he's now submitting the answer under session 228. The server says, nope, that CAPTCHA was never shown to this session. The result? A big red error. CAPTCHA incorrect, even if Kim solved it perfectly. That's why Kim uses a persistent session. With this one line, every request, whether it's visiting the login page, downloading the CAPTCHA, or submitting login credentials, is now sent using the same session ID, just like a real browser. And that means the CAPTCHA will match and the server will accept it, if it's correct. Now Kim's script behaves like a proper user. One session, one login, one CAPTCHA at a time. Without this one line, the entire attack would fall apart. With it, Kim's script now acts like a real browser, only faster, smarter, and automated. The next step is to create a function that does two things. First, downloads the latest CAPTCHA, and second, uses optical character recognition to extract the text from it. Here's the function, and we'll go through it line by line. The first line defines a function called getNewCAPTCHA. The second line simulates visiting the login page, just like a browser would. Like in the browser, visiting the login page starts a new session, generates a fresh CAPTCHA, and sets a session cookie. Without this step, the CAPTCHA Kim fetches next might be outdated or invalid. Let's look at it in the browser. If we go back to Sally login page, we can see that each time Kim reloads the page, a new session starts, a new CAPTCHA appears, and a session cookie is likely created. The call to session getLogin URL does the same thing programmatically. It's essentially the equivalent of refreshing the login page. Next, Kim sends a request to the CAPTCHA image URL. This returns the actual image that the server generated when the login page was loaded. The image data is stored in the content field of the response. At this stage, it's simply a stream of raw bytes. If the idea of requests, responses, or other HTTP concepts still feels unclear, my web hacking course linked above explains these topics in detail. The next line is where the magic starts. Bytes.io wraps the raw image bytes in a way that PIL, the Python imaging library, can understand. It's like turning a chunk of binary data into a real file. Then ImageOpen reads that file and creates a proper image object. Remember that image comes from PIL, as imported in the first cell. Now Kim has the CAPTCHA in a format that Python can actually work with. The next line is the core optical character recognition step. PyTesseract image to string takes the image and uses Tesseract to read the characters. The PSM7 option tells Tesseract, "I'm giving you a single line of text. No need to look for paragraphs or blocks. Just read the digits." This makes Tesseract faster and more accurate for numeric CAPTCHAs. Finally, the function returns two things: the actual image, if we want to display or debug it, and the extracted text, with any trailing spaces removed using strip. With this one function, Kim can now reload the login page, fetch a new CAPTCHA, solve it automatically, and prepare to use it in a login attempt. Next, Kim runs his new function to test it out. But he gets an error. Tesseract is not installed. Python is telling that Tesseract OCR is missing. And that makes sense. Remember, PyTesseract we installed with pip is just a Python wrapper. It connects to the real Tesseract engine that must be installed on the operating system itself. So Kim goes to the terminal and starts by updating his package list. Next, he checks if Tesseract is already installed. As you can see, it is not installed. To install it, Kim runs sudo apt install Tesseract OCR. The package manager then downloads and installs everything needed, including the Tesseract binary and its language models. Once installation is complete, Kim checks again by running Tesseract double-hyphen version. And this time, it shows Tesseract 5.5, confirming that the engine is now installed. It is fully set up and ready to be used in any script, including his notebook. With Tesseract installed, Kim goes back to the notebook and reruns the cell. And now, it works. The CAPTCHA image is displayed directly in the notebook. As you can see, it shows the digits 9312, with a few colored lines added to confuse bots. These lines are called noise, and they're meant to trip up automated OCR systems. In the next cell, Kim prints the text extracted by Tesseract. The output is 9312, a perfect match. Now let's run the function getNewCAPTCHA again. As we already mentioned, this is the equivalent of refreshing the login page in a real browser. The server will generate a brand new CAPTCHA image. And as you can see, this time, the image shows 9997. Another fresh code, with different noise and lines. Let's see if Tesseract successfully solved this one too. And voila! The output is 9997. Tesseract is fast, accurate, and incredibly powerful. An OCR tool that can handle even tricky CAPTCHA with ease. Remember, this video is for educational purposes only. Use these tools responsibly and only within a controlled lab environment or as part of an authorized penetration testing engagement. With this single step, Kim now has a fully automated CAPTCHA solver. He can repeat this process for every login attempt, no manual typing required. At this point, it's essentially game over for Sally's site. The next step, combine this with a username list and a password list, and test Sally's login form, one password at a time. We will see how this works, and more importantly, how such weaknesses can be prevented in the next video. If you found this video helpful or eye-opening, give it a like and subscribe for more deep dives into real-world cybersecurity flaws explained step by step. Thanks for watching and see you in the next episode. Until then, stay curious and stay secure. Bye-bye.